All right. The next class of differential equations we'll be considering is the class of first-order linear differential equations. So let's get right into it. A first-order linear differential equation is any differential equation of this form here. So it can be written in this way. And moreover, we ask that the a1 of x is not equal to 0. In fact, this is the reason why it's called first order, because then the highest derivative that appears in this differential equation is going to be given by just 1, because here's the first derivative. Okay, so this is a first order linear differential equation. And provided the a1 of x is not equal to 0, we can divide through by the a1 of x and get a differential equation in what's called standard form. So standard form is to say any linear differential equation that's in the following form. So firstly, if we divide through by a1 of x, the leading coefficient of y prime then will just be 1. And then here we'll get some different function, which we're going to call p of x times y. And then dividing g of x by a1 of x, we're going to get some other function, let's say f of x. Okay, so once we're in this position, once we have transformed this equation into into standard form, we're in a position to solve it, and the procedure is very, very straightforward. The first thing we need to do is to determine what's called an integrating factor. So integrating factor and this is also just abbreviated IF, and it's equal to e to the power of the integral of p of x dx. Okay, now when determining this function here, it is we're not trying to solve what functions of this shape. We're just trying to find one function which is obtained in this way. And so we may choose the constant here. Of course, performing this integration here will give us an arbitrary constant, and we may choose that constant equal to 0, because then that makes the integral really as simple as possible. And there are other simplifying assumptions we can make. Okay, so once we have determined the integrating factor, then we have a sort of the main formula for first order linear differential equations, and that's the following formula. If we take the derivative of the integrating factor multiplied by y, so take the derivative here. If you take the integrating factor, look, it's going to be some function of x, right? E to the power of the integral of a function of x is some function of x. Then y, we assume it's some function of x. So we take this derivative here, and then we're going to get if times f of x. Okay, so we won't go into why this is true, and we'll take this as it's given here, and just know that this is really the main formula for first order linear differential equations. Okay, so once we're in such a position, everything proceeds rather easily. We just integrate the right-hand side and divide by the integrating factor, and we would have solved the first order linear differential equation. So let's do 2 examples to see how this works in practice. So the question here is to solve the DE given by x times y prime plus y is equal to x squared. Okay, and we solve this differential equation over a given interval over 0 to infinity. Okay, so all positive real numbers. We want to find all positive valued functions to satisfy this equation. We're assuming that x here is going to be positive. Okay, so if we take this equation here, we first need to put it into standard form. So let's take this equation and turn it into one which is in standard form. So the way we do this is we need to divide by x, right? We need to take the leading coefficient here of the y prime. That's this function. If we go up to the top again, that's this function here, this a1 of x. And we need to divide the entire equation by this function. Okay, so here, given this, we just divide through, we get y prime plus 1 of x, y is equal to x. Okay, good. This is also fine, by the way, because we're assuming x is positive, so it's non-zero, and we can make such a division. Okay. All right, now in this situation, we have got to identify what is the... Okay, so if we go back to the standard form over here, we have to, in our specific equation, we have to identify what is the p of x and what is the f of x. So in this case, if we look back at our equation here, the p of x is just this function, and the f of x is just this one. Great, so we've identified this, and now there's always a very tricky thing, not very tricky, but a very common mistake is that if we have a minus here, the minus isn't taken into account in the p of x. So if this was a if we had, for instance, minus here, then p of x would be equal to minus 1 of x, just to be sure about that. Okay, so we're not in that situation, so our p of x is equal to 1 of x. So then our integrating factor is equal to e to the integral of p of x dx. And we can solve this because we know exactly what p of x is, so we take this integral. And this is just equal to e to the natural log absolute value x. Okay, and of course e to the natural log of absolute value x is just equal to x, absolute value x. Okay, and now this is equal to x. So we're just remember we're considering x on that's strictly positive. So absolute value x becomes exactly equal to x. So we can actually choose that the integrating factor is directly equal to x. Okay. Now we have found out what is the integrating factor. It is just equal to x. And we can now use the main formula, which is this one over here. So in fact, I'll just copy it. So we can use this formula here and plug in our specific values. So if I replace the integrating factor by what we've just calculated, we'll get x here. So x times y. The derivative of this is equal to the integrating factor, which again we've just calculated to be x, times f of x, which is, as we've just seen up here, x, just straight equal to x. So we can write here x. Okay, great. So we can now solve this. So this just means that x, y prime is equal to x squared. And so we can integrate both sides here. So the derivative of this function, this is the derivative of x times y. So that means that x times y, it's equal to the integral. Now we have the integral of x squared dx. So all possibilities of x times y is given by this, and this is just going to be equal to 1/3 x cubed plus the constant c, some arbitrary constant c which we don't know. And good. So we have found that x times y is equal to 1/3 x cubed. So we can solve for x. So we get y is just equal to this entire expression here divided by x. And so what we get is just going to be x squared over 3 plus c of x. Okay. So every solution to our equation will be of this form here. Okay, let's try a different example of a linear differential equation, and then that can be the end of this video. So the next example we want to solve is the following differential equation. We take here, so the question will always be solve the dE, but now I'm going to be change it a little bit. So solve the dE, and now I'll give you the dE, which is going to be 1 over 2x plus 1 y prime plus 2x over 2x plus 1 y is equal to e to the x. And now, so we're going to solve this dE over the entire interval. So I'll just say where x is going to be entire in the whole interval. So that means from negative infinity to infinity. That's our interval here. And subject to what's called initial conditions. And the initial conditions is always of this form. So we give you some number. In this case, it's going to be 0. And we tell you what y should be equal to. So y of 0, we want it to be equal to 2. Okay. So just to be clear again, what this is called an initial value. It tells you what the function's value is at a certain point, and so therefore is an initial value. Okay, so we can just solve the differential equation as we would normally. First we take the equation and we put it into standard form. So here we do that now. So we take this equation and we put it into standard form. And so what we're really going to do is just multiply through by this 2x plus 1 here, and then that will give us the leading coefficient of y prime equal to 1, of course. And so we'll just get y prime plus, oh, and then I should also say it cancels out nicely here in the second term to give us just 2x. So multiplying through the entire dE by 2x plus 1, we'll just get your 2x times y is equal to 2x plus 1 times e to the x. Okay, good. So now we should check something. We should check what are the functions. Just as in the previous example, we found what was px, what was f of x. Here we have to identify those. So here we can see this here, this function 2x is the p of x. This function here, sorry, not that all, the entire function on the right-hand side is the f of x. Okay. So, so here we've written our dE in standard form. We've identified the p of x, the f of x. So the next step is to determine the integrating factor. And this is equal to e to the power of p of x dx. And we can just go ahead and calculate this. This is e to the integral of 2x dx, which is equal to e to the x squared. Again, there's an arbitrary constant here, but we choose that to be equal to 0. Okay. So this is our integrating factor, nice and easy. And then we have the main formula. Again, for our first order linear differential equations, let me go up and fetch it. So we take this, put it here, and let's see what happens when we replace our integrating factor by the e to the x squared. So this will just become e to the x squared, and the integrating factor here becomes e to the x squared. And then the f of x, let me just go check what that was. You see it's 2x plus 1 e to the x. So 2x plus 1 e to the x. All right, so this is our differential equation, and now we have to solve this now. We have to determine what is the integral of the right-hand side. Okay. So the left-hand side here, e to the x squared times y. The derivative of that is equal to the integral here. And I'm just going to simplify the right-hand side a bit. This is just going to be equal to e to the x squared. Now, because we have a common base here, we can just add the exponents and we get e to the x squared plus x times 2x plus 1 dx. Okay. Okay, good. Now we have to solve this integral in usual way, and the way to do this, we can identify this integral as what method will work here. What method of integration will work is a u substitution with u equal to the exponent, because why? The exponent, the derivative of the exponent is given exactly here by this function here, and for that reason we guess that a u substitution will be good. And that's true because we take u equal to x squared plus x, then du will be equal to 2x plus 1 dx. And so this entire integral can be simplified a bit further into the integral e to the u du, which is just equal to e to the u plus c, which is equal to e to the x squared plus plus x. And sorry, I should just mention I've made a mistake. The derivative is equal to this, and so I should have taken the derivative away here. That's a mistake. Okay, so this function here, e to the x squared times y, is equal to this. Okay, now just a little bit of simplification to rewrite the same thing again. We have e to the x squared times y is equal to just e to the x squared plus x plus c. And so we can divide through by the e to the x squared term and get that y is equal to e to the x squared plus x plus c all over e to the x squared. And one just simplifies this to get e to the x squared plus c times e to the negative x squared. Okay. So now, once we're here, once we're in this position, we found the general solution to our RDE. This is, at this point, this is just the, we've solved the differential equation and we found its general solution. And we're not quite done because the initial problem had this, this initial value here. And we still need to incorporate that into our solution. We need to use those initial conditions to further refine this into a specific y, one function, not many. So the initial values, y of 0 equal to 2, give us some more information, and that is that if all functions look like this, all such y looks like this, right? Then when we plug in 0, we get the following equation. We get that, so y of 0 is of course e to the 0 squared is 0, plus c times e to the negative 0 squared, which is also 0. This must be equal to 2. But this is just 1 plus c is equal to 2. and this just means c is equal to 2. Okay, good. So that gives us the initial values, and finally that tells us exactly what y is. So finally we have that y is just equal to e to the x plus e to the negative x squared. Okay, and that solves this differential equation. And so going forward, we will assume that we know how to solve first order differential equations, and next up we'll talk about exact differential equations.